Hello everybody. Today we'll speak about the spectral theorem and in particular self-adjoint operators, unitary operators and orthogonal operators. So today's material is based on the lecture notes of April 21st, 28th, 30th and May 5th and 7th. So let me start by recalling the spectral theorem in the form we use it. So I'll write the statement, but not the proof. You can find the proof in the lecture notes. So in our setting, we have a vector space and an inner product on it, or a Hermitian inner product. So we want it to be finite dimensional. Either it's real and it has an inner product, or it is complex and has a Hermitian inner product. Okay. Suppose we have an operator and suppose that T is normal, and recall this was a condition saying that T commutes with its adjoint operator. Okay. Now the theorem says there exists orthogonal projections Pi such that several things happen simultaneously. So let me push this up a little bit. There are orthogonal projections such that, first of all, the image of each of these projections is one of the eigenspaces. This is eigenspace for the eigenvalue lambda I. The second is you can express the original operator T in terms of this projections and in a quite simple way. So T is lambda 1 P1 plus lambda 2 P2 all the way up to lambda K Pk, where lambdas are the distinct eigenvalues. So you have one of these projections for each distinct eigenvalue. So you have as many projections as eigenvalues. The third one, the identity is the sum of these projections. And Pi, Pj is 0 for all different pairs ij. Okay, so this is the statement of the theorem. Okay, now to make more sense of it, let's recall some facts. I'll push this up. So recall, we had some structural theorems about normal operators. First of all, a normal operator T is always diagonalizable. And furthermore, with an orthogonal eigenbasis. I mean, not just diagonalizable, but you can also choose the eigenvectors to be a perpendicular set, right? if you prefer to say this in terms of the eigenspaces, this means V is first of all the direct sum of these eigenspaces. So nothing is left out. I mean, this direct sum captures all of V, and furthermore, any two distinct eigenspaces are orthogonal to each other. So this is as good as one can expect in a sense. Okay. Another remark is Pi is a projection means by definition that Pi squared is equal to Pi. That was the algebraic definition of a projection operator. When you're saying this, you don't need any inner product, so there's no reference to an inner product. But if you want to say Pi is an orthogonal projection, this is, well, this condition, and Pi star equals Pi, meaning that Pi is self-adjoint, and since you have a star here, you have an adjoint that requires the presence of an inner product. Otherwise, you cannot make sense of the adjoint. Okay, so I mean, the projection itself doesn't need an inner product to be defined, but orthogonal projection does. Okay. So, well, one other nice thing which I should remark about the spectral theorem is that this is not a completely abstract theorem. Actually, one can express the PIs explicitly in terms of T. And to see this, you have to go to the proof of the spectral theorem, which I'll not go to, but I'll just say it. You just use so-called Lagrange polynomials. And the explicit formula is Pi, let me denote by small pi of t. Well, what you have to do is look at all possible t minus lambda 1I, so forth. You omit the ith one, so you come up to t minus lambda I minus 1I, then jump to I plus first one, and of course you go up to the end, so t minus lambda k I, and you have to somehow scale this with the difference of the eigenvalues. So what you write in the denominator is just a number, a non-zero number, and it is lambda I minus lambda 1 up to lambda I minus lambda I minus 1 here, and just you skip I and you go on. And the proof of the theorem actually is to make sure that this formula fits all this description. I mean, these items 1 to 4, 1 up to 4 are satisfied by these operators. Okay. Now, as a visualization, so, I mean, let me try to draw some kind of toy picture here. I mean, since I cannot do much more, I'll draw some two-dimensional picture. In 2 dimensions, this would be kind of, if you had 2 distinct eigenvalues, you would have one eigenspace here, another here, orthogonal to each other, right? And what happens is, okay, let's try to draw some red vector here. Okay, let this be V, for instance. I mean, P1 and P2 are just orthogonal projections to these subspace. So this is P1V, if you like, and this other orthogonal projection is P2V. Of course, if you add P1V and P2V, you get back V. So that's one consequence of the fact that P1 plus P2 in this picture is the identity. What about TV? Well, TV will be something else. Let me try to draw this with some other color, maybe green or something like that. Okay, let's say, just for instance, this is TV. Okay, just for demonstration purposes. Well, how do you express TV in terms of P1V and P2V? Well, what you have to do is multiply these by the eigenvalues. So the projection of this here may be not the same point, slightly different. So this slightly longer green vector is going to be lambda 1 P1V, and this other green component here is going to be lambda 2 P2V, and they add up to TV, and that's kind of a reflection of the fact that T is equal to lambda 1 P1 plus lambda 2 P2. Okay, so this should be kind of the picture that we should have in our heads, of course, but it's completely general, and even in cases where you might not want to picture it, it works. Okay. Now, let's do kind of a live example of this theorem, so we can sort of compute and see what's going on. Okay, let's choose something simple enough. So say A is the following matrix: 0, 4, 0, 4, 6, 0, and 0, 0, minus 2. Okay, let this represents an operator T on R3, R3 with its standard inner product. Well, R3 with its standard inner product, and this matrix represents T with respect to this standard basis. Okay, let's keep everything as simple as possible. Okay, so this is a certain operator on three-dimensional space. And now there's something which you can immediately observe. A transpose is equal to A, right? It's a symmetric matrix, and this immediately says that T should be self-adjoint. So it is normal. Why do I say this? I mean, so that I can use the spectral theorem. So spectral theorem works for normal operators. Okay, now to really see what's going on and to compute the projections, well, we first have to find eigenvalues. The characteristic polynomial is, let me denote by delta A or delta T, it doesn't matter. This is, of course, equal to determinant of xi minus A. Since everybody at this point knows how to make this computation, let me not spend time on it, but it comes out to be, please do it yourself, x plus 2 squared times x minus 8. So this operator has two eigenvalues. One is minus 2 with multiplicity 2, and the second eigenvalue is 8. Okay? Now we can again compute the eigenspaces in the usual way. Again, let me not do it, but just write the answer. So the eigenspaces are W lambda 1 is two-dimensional. It's the span of minus 2, 1, 0, and 0, 0, 1. And W lambda 2 is equal to the span of 1, 2, 0. This W lambda 2 is one-dimensional. So you have you can almost visually check that these two eigenspaces are orthogonal to each other. You can take dot products, but this is how it should be, right? Well, we have r cube is equal to w lambda 1 direct sum w lambda 2, and these two eigenspaces are orthogonal. So this is the orthogonal decomposition for this operator. Okay. Now the spectral theorem says we should have two orthogonal projections, P1 and P2. And if you use this formula with this Lagrange polynomials, well, in this case, you just have two eigenvalues, so it's rather simple. You just omit one in each case. So in the first one, you omit the first eigenvalue. It is t minus lambda 2I divided by lambda 1 minus lambda 2. Okay. Well, this is the operator, but let me write the matrix. Of course, you have to do a minus lambda 2I over lambda 1 minus lambda 2. And the matrix corresponding to this projection is minus 1 over 10 times this matrix minus 8, 4, 0, 4 minus 2, 0, 0, 0, minus 10. Please do this double checking yourself as well. Okay. Well, we see that P1 is a symmetric matrix, so P1 star is equal to P1, and P1 squared is equal to P1. You could, if you want, just check numerically as well. And likewise, P2 is small p2t, so this is t minus lambda 1I divided by lambda 2 minus lambda 1 this time. And well, let me write the matrix here. Matrix representative of this operator is 1 over 10 times 2 for 0. Okay, this should be, I guess, for 8, 0, and 0, 0, 0. Okay, I mean, there's quite a bit of things that you could double check just manually with these matrices. Well, check all the conclusions of the spectral theorem just to convince yourself. P1 squared is P1, P2 squared is P2, P1 plus P2 is you can almost see that if you add these two matrices, you really get the identity matrix. For example, 2 plus 8 here is 10 over 10 is 1 on that corner, and check all the other entries, please. And also, last but not least, minus 2p1 plus 8p2 should give you back the operator. And I also forgot p1, p2 is 0. So it's a nice and small exercise to convince yourself that this works. Okay? It doesn't say anything new, but just some reality check. Okay, now, yeah, this was just an example. The spectral theorem has far-reaching generalizations, especially if you want to go to infinite dimensions and put some analysis also in it. And that would more properly belong to some functional analysis course or some Hilbert space course. And here it has a crucial importance there too. Okay. Now, let's recall some consequences of spectral theorem. Now, it said, among other things, a normal operator is self-adjoint if and only if all of its eigenvalues are real and it is orthogonal or unitary Well, I'm saying both because it depends on context. In an inner product space or Hermitian inner product space, this happens if and only if its eigenvalues are all on the unit circle. Okay. And all such operators are unitarily diagonalizable. So what do I mean by that? They are diagonalizable, fine, but with an orthogonal set of eigenvectors. Or if you want to think about matrices, if A represents such an operator with respect to some basis, then you can make a change of basis. There exists unitary P such that A is equal to PDP star with D diagonal. Now, in the change of basis formula, we are usually used to A equals PDP inverse, right? Here it's P star, but P is unitary exactly means that P star is P inverse. So it's the same formula. The only additional thing said here is you can choose P not just invertible, but also unitary, which is much stronger. Okay, now I want to do some numerical example of this on some given matrix, how to find this P, okay? And since, okay, it would be nice to have a complex example, let's do something on two-dimensional complex space. So C2 with its standard Hermitian inner product. Let's look at the matrix A equals 2, 1 minus I, 1 plus I, 1, okay? Now, in this case, I should look at A star, which is not just A transpose, but A transpose conjugate, right? But if you do that, if you transpose and conjugate, then you get back A. So this means A is a Hermitian matrix, right? Okay, and this unitary diagonalization statement would apply. So you should be able to unitarily diagonalize it. So how do you do it? So we want to find a unitary 2 by 2 P and diagonal D such that A is equal to PDP star. Now this is not really very different from finding eigenvalues, eigenvectors again, but let's do it. So the characteristic polynomial in this case is determinant xi minus a. You can easily compute this. It turns out to be x times x minus 3. Okay, so lambda 1 equals 0 and lambda 2 equals 3. These are the eigenvalues. They are real, no surprise. The eigenvalues of self-adjoint operator or a Hermitian matrix must be real. Okay. Now the eigenspaces, again, you can compute directly. This time your eigenvectors will be complex because your matrix is complex. So these are complex one-dimensional. This is the span of minus 1, 1 plus I, and W lambda 2, span of 1 minus I, 1. Let me call this vector V1 and this one V2 for future convenience. Okay. Please do these computations yourself as well. Now, I claim that these two vectors are really orthogonal. How would you check this numerically? Well, you just have to do V1, V2, Hermitian inner product, and it's the standard product. So let's do it together. So it's minus 1 times, please be careful, 1 minus I bar, because it's the Hermitian product, plus 1 plus I times 1 bar, but 1 bar is 1. If you don't put the bars, you will get the wrong result. Well, 1 minus I bar is 1 plus I, so it's minus 1 plus I plus 1 plus I. This really gives you 0. Okay, these are orthogonal, fine. If you want a unitary matrix, you should also normalize them. So divide by their norms. So what are the norms? Well, let's find their squares. This is V1 inner product V1. Well, you have to do minus 1 plus 1 plus I, 1 plus I bar, right? And 1 plus I times 1 minus I gives you 2, so this will give you 3. And likewise, norm V2 square is V2, which is 1 minus I times 1 minus I bar, plus 1 times 1. Again, this is going to give you 3. So these vectors both have norm square root 3. And if you want to form this unitary matrix, write these vectors in columns, but before writing them, divide by their norms. And this is what you'll get. Minus 1 over square root 3, 1 plus I over square root 3, 1 minus I over square root 3, and 1 over square root 3. This is your unitary matrix. PP star will really give you I. You can double check, but that's all that we did. They are orthogonal and they have norm 1, so this relation will hold. And what is D? D is, of course, your diagonal matrix of eigenvalues, and A is equal to PDP star. It's worthwhile to directly check this and see that equality holds, just to convince yourself. Okay, now the final example that I want to discuss today is about a rotation in 3 dimensions. Before, let's recall a few facts about rotations. So, well, this is of course visually and physically also interesting because we see 3 dimensions around. So suppose we have R3 with standards inner product. Then this operator T is called a rotation. If T is orthogonal, first of all, you could say self-adjoint. In this context it is orthogonal, and it has determinant +1. An orthogonal operator can have determinant plus or -1. You want it to be plus. Okay, so the representing matrix A with respect to the standard basis must satisfy A times A transpose is identity, this is the orthogonality, and also determinant A equals +1. This will be the matrix conditions on the operator. Now we have a theorem for structural theorem for such rotations, and it says there exists an axis of rotation and a suitable basis, let's say B equals V1, V2, V3, such that with respect to B, the matrix for the rotation is of this special form. You have 1, 0, 0, 0, cosine theta minus sine theta, 0, sine theta, cosine theta. So V1 will correspond to, this first one will be the axis of rotation, and the plane spanned by V2 and V3, this two-dimensional plane, will be where the rotation is taking place. So the theorem says that all rotations in 3 dimensions look like this. All you have to do is to find the right basis. Now I want to do a concrete example of that, where you are given the matrix, how to find the axis and how to find the angle. So I'll write some specific 3 by 3 matrix here, but definitely not an arbitrary one. It's carefully chosen. Just 1/45. I'll write some funny integers: 37, 16, 20, minus 20, 40, 5, minus 16, minus 13, and 40. Okay, it's this very specific 3 by 3 matrix. Now, you might say, what's special about this? Now, please check by direct computation that AA transpose is the identity, and determinant of A is +1. It looks a little bit crazy because when you take the determinant, you'll get some very large number here apparently, but you have this 1/45 here, which will scale things down, and you really get 1. Maybe it wouldn't be, I mean, it's not a very illuminating exercise to do this by hand, but you could always feed this in a calculator for determinants or matrix products and check these immediately. Okay. So A is an so A represents a rotation. So the questions are: what is its axis? What is the axis of this rotation? And how many degrees is rotation? Right, a rotation should be of some certain amount, right? So what is the theta that you have for this particular matrix? Now, there's a clear procedure for doing this, and at this point it's not hard. Only the arithmetic might be a little bit daunting, so you might want to use some matrix calculators. Okay, so to solve this problem, first find eigenvalues and eigenvectors. Well, the characteristic polynomial with some routine calculation is x minus 1 times x squared minus 8 over 5x plus 1. You could either do this by a computer, or if you want to do this by hand, it's not hard. Let me tell you why. Now, everybody knows how to do determinant xi minus a and get a cubic polynomial here. Well, the additional thing that you need to know in this case is, since A is an orthogonal matrix, 1 is certainly an eigenvalue. No, right, that's given. So that polynomial that you obtain should be divisible by x minus 1. And once you know that, you can always divide and get this remaining strange quadratic polynomial, right? You don't have to anticipate this. I mean, you know that 1 must be an eigenvalue, since A is an orthogonal matrix. So, you can find the eigenvalues here. Lambda 1 is 1, and lambda 2 and 3, you compute the roots of this. They are complex valued 4 over 5 plus or minus 3 over 5 I. Now, if you try to place these on unit circle, let me use some different color. Well, one of them is here, and the others are on unit circle. I mean, if you square and add these up, this is norm 1, right? So these are complex conjugates. This is 4 over 5 plus 3 over 5i, and this is 4 over 5 minus 3 over 5i, and this is 1, right? All of them lie on the unit circle, and this is certainly expected, right? We are dealing with an orthogonal matrix. Well, the eigenvectors, let's find the eigenvector for lambda 1 equals 1. You can do this by direct calculation. Let me not repeat that. So it's spanned by this non-zero vector 1 minus 2. So you can check this directly. And once you find this, this gives you the axis, right? So W lambda 1 equals span V is the axis of rotation. Now, what is the axis of a rotation? It's the set of vectors which are not changed. So these have eigenvalue 1, so these are untouched by this rotation, then this is precisely the axis. If you want to find the eigenvectors for the complex eigenvalues, well, go ahead, fine, but we'll not do that. To visualize things, all that we have to know is, well, let's this be 3 dimensions, for example. Let's put here the axis somehow. Well, what we know is that everything is orthogonal, so this orthogonal subspace, this 2-dimensional space, will be left invariant, and that will be rotated, right? So let me say this is U and this is W lambda 1. U will be an invariant subspace. So if you want, you could go ahead, compute the complex eigenvectors and get back U from there, but it's all I have to do is to find a basis for this orthogonal complement. And we can do this actually really without computing new eigenvectors. Okay, so find a basis for orthogonal complement U and you could do this almost by trial and error. I'll just write the result. Now it's spanned by 2 to 1. and 2 minus 1 minus 2. So let me say these are v2 and v3, let's say. Okay, I mean, if you don't see that these are orthogonal ahead of time, I mean, you could always write the condition for being orthogonal to v and then find the solution of that linear system of equations. In any case, it's not difficult to find these vectors. Okay, now finally, to understand everything, we want to find angle of rotation, right? So to find angle of rotation, there's a slick way to do this. Find the angle, for example, between one of these vectors, v2, let's say, and what happens to it after the transformation, so AV2, right? We could compute V2, AV2, and the angle between them. This is a very straightforward calculation because AV2, you just have to do matrix multiplication. The answer you get happens to be 1 over 5, 14, 5 minus 2. Please double check my calculation. And the angle between these two vectors, let's say cosine theta, we have the usual angle formula. V2 inner product AV2 divided by norm V2 and norm AV2. There's a bunch of calculations here. So what you get for V2 AV2 happens to be 36 over 5. Now the norm of V2 remember is 2, 2, 1, so square them, add them up, 4, 8, 9, square root is 3, so this number is 3, and AV2 should have the same length because this rotation will not change the length of V2, so you divide by another 3, and the number that you get here is 4 over 5. So theta should be the angle whose cosine is 4 over 5. It's approximately 37 degrees. So now we have some kind of perfect understanding of this rotation. It has an axis, let me look up, okay, spanned by 1 minus 2, 2, you know its direction, and the angle of rotation is 37 degrees. You might ask counterclockwise or clockwise. Well, make a last check about the V3 and you can figure that out easily, and you geometrically understand what this rotation is doing. Okay, so this was an example of dealing with a rotation. Of course, in a practical, this was a kind of textbook example. For another example, you might not have nice integers like that, but you can always follow the same strategy and do the computations with a computer. This is quite easy to handle. Okay, that's all for today. Thank you for listening.